In the realm of algebraic geometry and algebraic combinatorics, the study of flag varieties, Schubert varieties, and their corresponding structure constants is paramount. The quantum cohomology ring QH** operator, FLN, encodes important information in theoretical physics and is a deformation of the cohomology ring, with its structure constants extending the generalized Littlewood-Richardson numbers in a quantum direction. These constants can be calculated using the quantum Bruhat graph, a graphical representation of the quantum Monk's rule, which has rich algebraic and combinatorial properties. The quantum Bruhat graph gives rise to the tilted Bruhat order, a central combinatorial object of interest. This paper presents two main results. First, it provides an explicit combinatorial formula for the minimal weight between any pair of permutations UTOV in the quantum Bruhat graph, as well as an Ehresmann-like characterization for the tilted Bruhat order. These results were also obtained independently via toric-Schur polynomials and geometric methods, but this paper offers a novel, independent, and combinatorial proof. Second, the paper introduces the concept of tilted Richardson varieties and open tilted Richardson varieties, which reduce to the well-known Richardson variety if U is less than or equal to V in the Bruhat order. These varieties are defined using rank conditions, cyclically rotated Richardson varieties in the Grassmannian and multiplucker coordinates. This novel geometric interpretation of intervals in the tilted Bruhat order offers a more classical flavor and sheds light on the connection between quantum cohomology and classical geometry. The paper explores the combinatorics of the quantum Bruhat graph, providing a comprehensive understanding of the structure constants of QH** operator, FLN, and their relationship with the tilted Bruhat order. It also delves into the geometric properties of tilted Richardson varieties, including their stratification, dimension, and closure. This research contributes to the ongoing quest for a combinatorial interpretation of the three-point genus 0 Gromov-Witten invariants and deepens our understanding of the intricate relationships between quantum cohomology, combinatorics, and geometry. The paper discusses the concept of quantum Bruhat graphs and tilted Richardson varieties, which are central geometric objects in the study. A quantum Bruhat graph is a weighted directed graph on the symmetric group Sn, with two types of edges, one with weight 1 and another with weight j. The latter occurs when there is an inversion between elements I and j in the permutation W. The authors also introduce the concept of cyclic intervals and their connection to the quantum Bruhat graph, as well as the automorphism of the unweighted quantum Bruhat graph under the long cycle tau. The paper also highlights the properties of shortest paths in the quantum Bruhat graph, as established by Postnikov, 12. These paths have a unique weight, which is divisible by the minimal weight Qd, U, V, from U to versus. This minimal weight is an N1 tuple, and it is essential for understanding the geometric properties of tilted Richardson varieties. In the context of the quantum Bruhat graph, the authors provide an example illustrating the existence of multiple shortest paths with the same weight. This example demonstrates the importance of considering the weight of paths in the quantum Bruhat graph, rather than just their length. The paper concludes by mentioning its organization, which includes sections on background information, definitions of open tilted Richardson varieties, and their geometry. The research presented in this paper contributes to the understanding of quantum Bruhat graphs and their relation to geometric objects such as tilted Richardson varieties. It provides new insights and techniques for analyzing these geometric properties, which are crucial for computations in quantum cohomology and K-theory of flag varieties. Here is the combined summary of pages 5 and 6 of the research paper. The authors introduce the concept of tilted Bruhat order, a graded partial order on the symmetric group Sn, defined as W is less than or equal to UV if and only if there exists a shortest path in the quantum Bruhat graph from U to versus that passes through W. The tilted Bruhat interval, W, V, U is defined as the set of all x in Sn such that W is less than or equal to Ux is less than or equal to UV. The authors also introduce the root system of type N1, consisting of positive roots phi plus and simple roots increment, and define a reflection ordering as an ordering of phi plus such that EIK appears in the middle of AA and eject for all I less than j less than k. The authors then move on to define the Grassmannian GR, K, N, as the space of k-dimensional subspaces of Cn and introduce the Plucker embedding, which sends a subspace V with basis vectors version 1, Vk to the projective equivalence class of V1 and Vk in lambda k, Cn. The Plucker coordinates of V are defined as pi1, ik, V, equals, -1, L, sigma, p sigma, I1, sigma, ik, V, for any permutation sigma in Sk. The authors also define the Plucker relations, which are used to define the variety gr, k, n, as the zero locus of the ideal generated by these relations. Furthermore, the authors define the complete flag variety flat n as G, B, where G equals GLN, C, and B is the Borel subgroup of GA.GB and G, B is identified with a flag F equals 0 equals F0 subset of Fn1 subset of Fn equals Cn, where Fk is the span of the first k column vectors of any n times n matrix representative MF in GB. The multi-Plucker embedding is defined as the composition of the Plucker embeddings of the Grassmannians gr, k, n, for k equals 0, n. The authors also define the incidence Plucker relations, which are used to define the complete flag variety flat n as the zero locus of the ideal generated by these relations. The paper discusses quantum Bruhat graphs and tilted Richardson varieties, focusing on two special cases of equation, 2. In these cases, the incidence place diaresis-Ucker relations are rewritten for convenience. The Schubert and Richardson varieties are also explored, with the Schubert cell defined as the Borel orbit of EU and the Schubert variety as the closure of the Schubert cell. The paper then delves into the Grassmannian Schubert varieties and cells, defining them based on the dimension of certain subspaces. The relationships between these varieties and cells are detailed, including their stratification and the conditions for their non-emptiness. The Richardson varieties are also discussed, which are defined as the intersection of Schubert and opposite Schubert cells. The paper concludes by highlighting the importance of these varieties and cells in understanding the geometry of algebraic varieties. In the context of quantum Bruhat graphs and tilted Richardson varieties, the research discusses the combinatorics of the quantum Bruhat graph, focusing on minimal weights in the quantum Bruhat graph. A key theorem provides an explicit formula for the minimal weight Qd, U, V, from any pair of permutations U and V in Sn. This involves the construction of lattice paths and their depths, which are used to compute the minimal weight. The proof relies on a specific reflection ordering and the uniqueness of directed paths in the quantum Bruhat graph with strictly increasing labels. The research also utilizes the Brenti-Fomin-Postnikov tool, labeling each directed edge with A-EJ, to analyze the paths. The study's technical depth and precision are notable, particularly in its use of definitions, such as the shifted Gale order, and its detailed explanations of lattice paths and their roles in the computation of minimal weights. In the context of quantum Bruhat graphs and tilted Richardson varieties, this research paper delves into the weight accumulation process. It is demonstrated that the weight of a path, denoted as Wt_1, U, V, equals Q_1 Q_2, Q_ pk1, if U, pk, less than U, pk1, and U, pk, greater than V_1 plus 1 U, pk1, and equals 1 otherwise. The paper also shows that the weight of a minimal weight path from U to V, denoted as Qd, U, V, is equal to depth, U, V, the depth of the lattice path P, U, V. The paper then moves on to characterize the tilted Bruhat order, a concept introduced by Brenti-Fomin and Postnikov. A key consequence of Theorem 3.3 is a succinct description of the tilted Bruhat order, which is presented in Theorem 3.9. To build intuition regarding the relationship between the shifted Gale order and the lattice path construction, the authors introduce two lemmas. The first lemma, lemma 3.7, states that for any A, B subset of n, with A equals B, there exists R element of n, such that A is less than or equal to _RB. This implies that the lattice path P, A, B, passes through R1, depth, A, B, where depth, A, B, is the depth of the lattice path P, A, B. The second lemma, lemma 3.8, explains the relation between different shifted Gale orders. It asserts that if A is less than or equal to _RB and A is less than or equal to _R B for some R element of n, then the intervals A, B, _R equals A, B, _R in the shifted Gale order. Furthermore, for any I element of A, B, _R, the authors show that A intersection R C equals I intersection R C equals B intersection R C, where denotes the cardinality of a set. These lemmas are crucial in understanding the relationship between the shifted Gale order and the lattice path construction, and ultimately contribute to the characterization of the tilted Bruhat order. The paper also provides a detailed analysis of the lattice paths P, A, I, and P, I, B, for I element of A, B, _R, demonstrating that these paths reach their lowest points at both x-coordinates R and R. This analysis further strengthens the connection between the shifted Gale order and the lattice path construction, ultimately leading to the succinct description of the tilted Bruhat order in Theorem 3.9. Here is a combined summary of pages 13 and 14 of the research paper. The authors establish equivalence between four statements regarding the tilted Bruhat order on the symmetric group Sn. Specifically, for U, V, W element of Sn, the following are equivalent. W is less than or equal to UV. W element of U, V, for all sequences A equals A1. And one such that U1, UK, is less than or equal to AC, V1, VK, and for all K element of N1, U1, UK, is less than or equal to AC, W1, weak, is less than or equal to AC, V1, VK, and there exists a sequence A equals A1. And one such that for all K element of N1, U1, UK, is less than or equal to AC, W1, weak, is less than or equal to AC, V1, VK. The proof involves leveraging the automorphism tau of the unweighted quantum Bruhat graph and analyzing the exponent vectors of shortest paths. The authors then shift their focus to geometry, aiming to provide three equivalent definitions of open, tilted Richardson varieties 2, V and T hollow bullet U, versus for any pair of permutations U, V element of Sn. These varieties will later be shown to provide a geometric meaning to the tilted Bruhat order. The three definitions utilize rank conditions, cyclically rotated Richardson varieties in the Grassmannian, and multiplucker coordinates. The authors first work with 2, V, A and T hollow bullet U, V, A and then demonstrate that they do not depend on the choice of sequence A. The first definition of tilted Richardson varieties is motivated by the characterization of the tilted Bruhat order. It involves specifying rank conditions on the dimensions of projections of flags F element of FLN. The authors also provide an alternative visualization of tilted Richardson varieties using matrix representatives and submatrices. This facilitates the computation of ranks and enables a more intuitive understanding of these varieties. The research paper discusses quantum Bruhat graphs and tilted Richardson varieties, focusing on their properties and relationships. It begins by introducing quantum Bruhat graphs and their connection to Richardson varieties. The authors then define cyclically rotated Richardson varieties, which are instances of positroid varieties. They prove that these varieties can be defined via vanishing of certain Plucker coordinates. The paper also explores the intersection of these varieties with flag varieties, leading to the conclusion that the tilted Richardson variety is independent of the choice of a sequence. The authors utilize various lemmas and propositions to establish these results, demonstrating a deep understanding of the underlying mathematical structures. The paper's technical depth and precision make it a valuable contribution to the field of algebraic geometry and its applications. The research paper discusses quantum Bruhat graphs and tilted Richardson varieties, focusing on their properties and relationships. It begins by explaining the definition of quantum Bruhat graphs and their connection to tilted Richardson varieties. The authors then delve into the proof of a lemma that implies the row spans of certain areas in a figure are independent. This independence is crucial for understanding the properties of the tilted Richardson varieties. The paper also introduces a corollary that follows from the lemma, which is used to denote the open tilted Richardson variety. Further, it discusses the vanishing of Plucker coordinates and its implications for the varieties. The authors then present a theorem that defines the tilted Richardson variety as the intersection of two sets, one based on permutations and the other on the vanishing of Plucker coordinates. The paper concludes by exploring geometric properties of the tilted Richardson varieties, including their stratification by open tilted Richardson varieties. The authors provide several lemmas and theorems to support these claims, demonstrating a deep understanding of the mathematical concepts involved. The research paper discusses quantum Bruhat graphs and tilted Richardson varieties, focusing on the dimension of T-hollow bullet U, van Tu, V, which is shown to be L, U, V, the distance between U and V in the quantum Bruhat graph. It analyzes T-hollow bullet U, V from different charts, including permutations and their opposite Schubert cells. The paper introduces the concept of tilted Roth diagrams, D down pointing arrow A, U, and D up pointing arrow A, V, and their relation to the parametrization of omega hollow bullet U. It also defines a set of equations, IU, V, A, for every pair of permutations and choice of A, which is crucial for the dimension calculation. The paper distinguishes a particular choice of A as flattening sequences, U, k-1, is less than or equal to AKV, k-1, for all k element of 2, n-1. This research contributes to a deeper understanding of quantum Bruhat graphs and their applications in algebraic geometry. We begin with the concept of quantum Bruhat graphs and tilted Richardson varieties, where the choice of A's maximizes the number of equations in IU, V, A. This leads to lemmas 5.10 and 5.11, which establish the existence of flat A's and the number of equations in IU, V, A. The proof of lemma 5.11 involves induction on L, U, V, and a detailed analysis of column K in the diagrams D up pointing arrow A, V, and D up pointing arrow A, X. Moving on, we discuss example 5.12, which illustrates the proof of lemma 5.11, and proposition 5.13, which shows that T hollow bullet U, V equals U omega hollow bullet I intersection V omega hollow bullet I intersection V, IU, V, A. This involves two types of equations and the vanishing locus of equations in IU, V, A. The proof of proposition 5.13 includes a demonstration of subset equal and superset equal, showing that T hollow bullet U versus is equal to the vanishing locus on the chart U omega hollow bullet id intersection V omega hollow bullet id. We discuss the properties of quantum Bruhat graphs and tilted Richardson varieties, focusing on their incidence place diaresis-Ucker relation. Specifically, we examine the case where I, E, AEO, / is greater than or equal to AKU, K, or I, E, AEO, / is less than or equal to AKV, K. Showing that in both scenarios, the right-hand side of the incidence place diaresis-Ucker relation vanishes. This leads to the conclusion that pi vanishes on F. The proof involves two cases, where either I is greater than or equal to AKUK or I less than AKUK, demonstrating the vanishing of pi minus I in each scenario. This result is crucial for understanding the equidimensionality of tilted Richardson varieties, as shown in theorem 5.14. The theorem states that tilted Richardson varieties are equidimensional of dimension L, U, V. The proof involves a contradiction argument, demonstrating that every irreducible component of tilted Richardson varieties has dimension at least L, U, V, and then showing that the dimension cannot exceed L, U, V. The section concludes with a discussion on controlling the dimensions of quasi-affine varieties, including a lemma on the dimensions of quasi-affine varieties and their intersection with certain charts. The research paper discusses quantum Bruhat graphs and tilted Richardson varieties, focusing on the properties and relationships between these entities. It begins by establishing an equivalence between two sets of equations, demonstrating the connection between quantum Bruhat graphs and tilted Richardson varieties. The paper then introduces corollary 5.19, which states that under specific conditions, a certain summation of equations equals 0. This corollary is used to prove proposition 5.20, which shows that for any flat A, the set 2 V intersection U omega hollow bullet it intersection X omega hollow bullet IDIS equivalent to the set V IU V A X. The proposition is crucial in understanding the relationships between different varieties and graphs. The paper concludes by discussing the properties of the set V IU V A X and its connections to other sets through equations and summations. Throughout, the paper employs mathematical concepts and equations to demonstrate the relationships between quantum Bruhat graphs and tilted Richardson varieties, providing a comprehensive overview of their properties and interactions. The paper discusses the concept of quantum Bruhat graphs and their relationship to tilted Richardson varieties in the context of quantum K-theory. It begins by introducing the quantum Bruhat graph, which is a directed graph with vertices corresponding to elements of a Weyl group, and edges defined by certain conditions involving the Bruhat order. The authors then define the tilted Richardson variety as the intersection of two Schubert varieties, and they show that this variety is equidimensional with dimension given by the length of the longest chain in the quantum Bruhat graph between two elements of the Weyl group. The authors also introduce the notion of quantum K-theory, which is a generalization of classical K-theory that incorporates quantum parameters. They define quantum Schubert classes and quantum Bruhat graphs, and they establish connections between these objects and the geometry of Schubert varieties and tilted Richardson varieties. The main result of the paper is Theorem 5.22, which states that the quantum K-theory of a cominuscule space can be expressed as a sum over certain subsets of the quantum Bruhat graph. This result is proved using a combination of algebraic and geometric techniques, including the use of quantum Schubert classes, quantum Bruhat graphs, and the geometry of Schubert varieties and tilted Richardson varieties. In addition to this main result, the paper includes several other key results, such as Proposition 5.21, which shows that the quantum K-theory of a cominuscule space is equidimensional, and Theorem 5.22, which provides a formula for the quantum K-theory of a cominuscule space in terms of quantum Schubert classes and quantum Bruhat graphs. The paper concludes with a discussion of potential future directions for research in this area, including the study of non-cominuscule spaces and the development of new algebraic and geometric tools for understanding quantum K-theory.